Right, welcome back everyone. I know that the exam is around the corner, so I try to answer as many questions raised by students before the exam. And then today I'm going to compile few questions related to complex number. Right, so here this is one of them. Let's go through that. Now we have a complex number 3 minus I denoted by U, and then its complex conjugate is denoted by U star here. Now on the Argand diagram with the origin O, show the point ABC representing the complex numbers U, U star, and U star minus U respectively. And then thereafter, by or through observation, in this case, you are going to determine what type of quadrilateral does the OABC represent here. All right, so let's take a look at number one. All right. Now, first of all, we have been given u equal to 3 minus I, and then therefore the complex conjugate, which is denoted by u star here, is given by 3 plus I itself. And then making notes that I square is equal to negative 1. All right, because the u is a complex number, right? And then the O is having a coordinate 0, 0. We all know that, right? And then lastly, we are going to determine the u, um, the complex conjugate for u and this, right? So the difference between the complex conjugate and its complex number here, that should not be any problem. All right. 3 minus I here, and then that you could easily get this answer here, which is 0 plus 2I. I just purposely put a 0 there, just to remind you that the point C is represented by 0, 2. Okay, so this is how it look like. Now I have already plotted this on the software itself, so let me show you how does it look like. Okay, now you can see that from here we have the point, the origin here. We have the point A representing the complex number u, and then we have the complex number, the complex conjugate u, which is here. And then lastly, we have the difference between the complex number conjugate and its complex number u. So u star minus u here. All right, now this is what we have. Okay, now we are going to uh, observe all the points here. We have all A, B, C here. We're going to identify what sorts of quadrilateral does this OABC represent, right? Now we can tell very easily this quadrilateral represent parallelogram. All right, so this is a parallelogram. Therefore, we can say that, okay, we can say that OABC represent a parallelogram, right? You can observe that quite easily. The AB is a vertical line which is parallel to OC, and then BC, you can determine the slope of BC quite easily, which is exactly the same slope as OA. So therefore, it is a parallelogram here. All right. So I hope that the first part is clear. Then the second part, showing your working and without using calculator, express the fractions or the ratio between the complex conjugate and its complex number, and then we need to represent this in this particular form. So therefore, let's look at the second part. So second part is quite direct. It's just complex conjugate with its complex number. Complex conjugate is 3 plus I. Then this is 3 minus I here. Now, by using a bit of rationalization technique, which would be here, we rationalize it using the complex conjugate of 3 minus I. All right, now by simplifying this, we will get, let me see, a 9. This one is a 9 plus a 6i. You can see that quite easily. And then lastly, you have I square. The denominator is 9. 9 itself minus I square. As I mentioned before, the I square is -1. Therefore, you must be very careful with the I square here. Right. Now, knowing that this is -1, we have 8 plus 6i over the denominator will become a 10. Right. Now, in this case, you can either leave it as like 0.8 plus 0.6i, or you can leave it as fractions. Right. So there you have it, question 1 and question 2. All right. So I'm going to pause here for a while, let you organize your thoughts, and then compare your answer with what I got so far here. Okay, so I hope that is clear. Now, next, we can look at number 3 directly here. Let me clear everything here. Okay, all right, let me come back in. All right, let's take a look at question 3 here. By considering the argument of this ratio, we have obtained this argument. Sorry, we have already obtained the ratio for this complex number, which is u star over u here, and then that is 0.8 plus 0.6i, and then I have represented this complex number. I will label this as w, this complex number on the Argand diagram. So you can see that it is represented by the point D here. This is w, right? And then its argument, I can label its argument as, so I can label this as theta. So that argument of this complex number is theta here. All right. Now, just a bit of theory to prove it to you why we have this particular um, property of the ratio or complex number. So take for instance, if you are interested to investigate the arguments of complex number here, there is a property related to this argument. It is stated that argument of this is the same as argument of u subtract off with argument of u here. Right. Now, where does this actually came from? So here I just briefly show you a very simple idea behind how this property was derived from. All right. Now we know that u star, or the complex conjugate, can be represented by using Euler form. So we can say that it has a magnitude of R1, and then I, let's call this I alpha, whereby the complex number u can also be represented by using its own magnitude and its own argument. And then when we take the ratio of this, that would be R1 EI alpha over R2 EI beta here. And then with a bit of simplification, we can group the magnitude together, and then by applying the exponential rules, we have this alpha minus beta here. And then there you have it. What you are looking at right now is the argument of w. Argument of w is actually alpha minus beta, because this one is the argument for w here. But then again, you are asking yourself, what is alpha then? So alpha is the argument of the complex conjugate, whereby beta is the argument for u. Now that's how we can relate to this property. And then knowing this property, we can answer these questions quite easily, right? So when you're ready, you can organize your thought. This is where this property came about. Now we're going to apply this property directly. So let me clean this up here. We don't need this anymore. All right, so from here, we're going to apply this directly, as I mentioned before. Now the argument for the complex conjugate. If you refer to the complex conjugate here, this is the complex conjugate U star here. This is U. Now the argument for complex conjugate, if I label it alpha here, this one is the beta. All right. Now alpha argument of the complex conjugate is given by alpha, which is or which can be represented in the form of tangent inverse. That is, you can see that here. This is 1 unit and then to 3 unit. So therefore, it is a ratio of the inverse tangent 1/3, right? Whereby the beta is the argument for u, for the complex number u, and then that can be represented by the same ratio here. The only difference is beta is a negative angle when we measure it clockwise direction. So therefore, we're going to put a negative tangent inverse. Now, anyway, they have the same ratio, so it's 1/3 also. And then finally, we're going to conclude that the difference between this. So therefore, you can see that the difference between this is just 2 tangent inverse. But anyway, the argument, if you refer to this particular complex number that we have already obtained, that is representing this ratio here. Now that argument of W from the graph itself, which is represented by theta, is actually given by the ratio of tangent inverse because it's 0.8 and 0.6 here. So that is 0.6 over 0.8. Now, of course, you can simplify that, should not be a problem. That is just 3/4. And then we know that the argument W is the same as alpha minus beta here, whereby the alpha is the argument of complex conjugate, and then that's how we get this relationship. We're going to substitute whatever result that we have obtained so far. The alpha is tangent inverse 1/3, whereby the beta is negative. Negative become positive here. And then finally, we can conclude that this is the same as 2 tangent 1/3, whereas the argument for W, we have also found out that argument for W is tangent inverse 3/4. And then that complete our proof here. Now, I hope that that is clear for this question here, right? I'll proceed on to the next question shortly. All right, welcome back to the second question requested by the students here, which is also a complex number. Now, anyway, for those students who are interested to know which past year paper does this question belongs to, do check out the description in the video itself to find out. All right, so let's get started with solving this question 11 here. Now, A, we are given two complex numbers Z and W. We are going to solve this simultaneous complex number and then eventually obtain the complex number for Z and W in the form of X plus IY, or rectangular form. Right? So let me scroll it up a bit here. We don't really need to refer to the first part. Okay, now solving this is quite an easy task for most of you, right? Because this is just solving it simultaneously, right? Let me rewrite the equations and then label them correctly. All right, so from here we have Z plus 1 plus IW equal to I, whereby I need to denote again the I square, which is a complex number, equal to -1. Now we're going to label this as equation number 1, and then the second one being 1 minus I Z plus IW equal to 1 here. That will be our second equation. Now in this case, if we look at the equation itself, I think personally it's easier to eliminate Z itself for those of you who are using elimination method, if you wish to use substitution methods, by all means you can go ahead. All right, now I'm going to apply elimination method by first of all multiplying the first equations by 1 minus I. Okay, now that would yield 1 minus I z. All right, and then let's try to simplify a bit before I put the label on. Then this one you can actually key into a calculator if you have no idea how to do this manually. Okay, that is typically it's just a 2. Yeah, it's just a 2. So in this case, it's just 1 plus 1. So it's just a 2w is equal to, this one we can simplify that. We have 1 plus I here. That will be our third equations here. We are going to solve 2 and 3 now by using elimination. Okay, so that would be now it's either way. So take for instance, I'm going to take 3, subtract off with number 2, and then therefore z can be eliminated. What we're left with is just 2 minus I w is equal to, this is 1 anyway, therefore if we subtract this we get an I instead, and then w would be equal to I over this. And then don't forget we need to rationalize this with its complex conjugate, and then that will be a 4 plus a 1 here. That would yield a negative 1 plus a 2i divided by 5. Or you can just write down w as negative 0.2 plus 0.4i there. And then there you have it. That is the first complex number, w. And then to get the second complex number, it will be quite easy. Take for instance, I'm going to retrieve that complex number z from equations number 1. I would get z equal to I minus 1 plus I w. So w that I have is here. And then with a bit of expansion here, I better put a square bracket there in case I make a mistake here. We have 0.2, and then what else? 0.4i minus 0.2i, and then finally we have 0.4 there. I have already removed the I square here, and then finally we have we can combine. This is 0.2i, and then the real parts will become negative 0.6, which become a positive 0.6, and then the imaginary parts is 0.2i, which is negative 0.2i here. Right, so negative 0.2 become 0.8i after we subtract that off from I itself. Okay, so I hope that is clear up to this point. This is the complex number z and the complex number w. Right, so we are done. I hope that's clear. We're going to move on to the second section shortly. All right, let's take a look at the second question here. We have the complex number u and v are given by these two complex number. In an Argand diagram, u and v are represented by the points A and B. A third point C lies in the first quadrant and is such that it satisfies these two property. It has a magnitude of BC is twice the magnitude of AB, and then the angle ABC is 90 degree. We need to find out the complex number Z represented by C, giving your answer in the form of x plus iy, where x and y are real and exact value here. Right now I have already prepared this. I'm going to show it to you. Now initially this is where the point A is located. Point A is given by 1 unit to the right, and then 3 units up here. So that's what we have. Let me scroll it up a bit more so that you can see there. All right, so this is A, and then point B is 3 unit there, and then 2 unit up here. All right, So that's what we have. And then C lie in the first quadrant. Yes, you can see that is first quadrant. It has to be 90 degree. So ABC has to be a right angle triangle. Sorry, right angled here. It has to be a right angled here. All right. So this is where the C is located. The length of BC is twice the length of um, AB here, twice the length of AB. So I roughly sketch it in such a way. All right. Now we're going to figure out what would be the complex number Z represented by C here. There are many ways to do this. All right. You can either use um, the I would say the first impressions that you would get is you would rather use coordinate geometry approach. All right, even though this is a complex number question, you can use coordinate geometry approach to obtain to obtain the coordinate C, right? But I think most of the time when you read a complex number question, you may not realize that you can actually apply coordinate geometry method. Yes, you can actually use that. It's a bit lengthy because you need to solve um, simultaneous equations at the same time also. So it's quite tedious, it's quite lengthy. I will not advise you to do that, all right? But we do can actually find out, right? So later on, I will spend a little bit of time to show you how we can use coordinate geometry, and then at the same time, we can also use the vector method to find out the coordinate for C here, all right? But for this time being, I'm going to show you how to use the geometrical method, which is more of the approach utilized by complex number here. By looking at this setup here, I'm going to let you guys roughly know that, okay, what we are looking at. We are looking at like, okay, now bear in mind at this point of time in the exam, you may not know the exact coordinate for C. So this is just a rough sketch. I might actually landed on 6 here, but don't take the 6 as the answer. We're going to verify it algebraically and through geometry here. And then now let's call this x coordinate C. So we will call this coordinate as xc. So xc is actually from here to here. Now that is the coordinate for C, coordinate x for C, and then coordinate y for C, I will label it as yc then. So how do we get the coordinate y for C then? So coordinate y for C, again, I like to stress that this is not the answer, just a rough sketch here. So yc is over here, this is yc, the vertical height. That is yc. Okay, how do we get the YC? It will be quite simple because we know the coordinate for B, which is 3, 2 here. From here, we know that YC, I'm going to write down YC here. YC is actually given by the 2 plus an extra increase of C here. All right. So that's how it look like at this point. Okay. Now, how are we going to find the extra increase of YC? Okay, so I'm going to write it down here. There's extra increase of YC. We can find out the length for AB quite easily. Now, let me call this length of AB. I will say let length of AB be Um, let's just call it as P then. It's easier to relate. Let's just call it as P. Therefore, if the length here is P, then this one must be 2P then. Okay. Now that's the one that we know of, all right? And then next, we can make use of the argument. So take for instance the argument for AB, right? So right here we will let the angle be theta here. So the angle between this line and the horizontal line is theta, and then we know that this is 90 degree. Now the relationship between theta and alpha is very obvious. We know that theta plus alpha must be equal to 90 degree. And then knowing that this is the case, we can change it to alpha is equal to 90 degree minus theta, right? All right, now that's what we have. Now just a bit of recap on trigonometry ratio here. If we were to use sine alpha, in this case, it will give us cos theta instead. And then it's the same goal for cos alpha. That will be sine theta itself, right? How can we find out the sine and cos theta in this case, right? All right, so from here we can obtain the trigonometry ratio sine and cosine theta just by looking at this right angled triangle here. We can denote the cosine theta. Okay, we can denote the cosine theta as 2 over p, whereby the sine theta as now sine theta is actually this length here, which is 2 sec 3 minus of 2, right? So therefore, the ratio of sine is 2 sec 3 minus 2 over p. Now that will be the trigonometry ratio for sine theta and cosine theta. And then by using this, we can work out the increase of the y coordinate c here as 2p sine alpha, 2p sine alpha, and then that will be 2p. Our sine alpha is equal to cosine theta, so sine alpha is the same as cosine theta, so we can look at cosine theta here, 2 over p. You will notice that we can remove the p directly, therefore it's a 4. And then from here we can conclude that the y coordinate for c is 2 plus a 4, which is a 6. Okay, now we're going to work out the x coordinate for c. For x coordinate for c, that is given by 3 plus the small increments of c here, right? Which we can obtain it using the same strategy as above. That will give us 3 plus the increment of this x coordinate is given by 2p cosine alpha. And then cosine alpha is sine theta, which is given by this. Therefore, we're going to rewrite that as 2p 2 sec 3 minus 2 over p. Okay, therefore we're going to simplify this. We will get 3 plus 4 sec 3 minus a 4, and then eventually we have a 4 sec 3 minus a 1 here. And then there you have it, the coordinate for C. But we need to write this coordinate for C in a complex form. Then we can conclude that, therefore, the complex number Z that represent this coordinate here is given by, all right, now the X, which is 4 sec 3 minus 1, plus the Y, which is 6I here. And then there you have it. Right, our next question is here. Without using a calculator, solve the equation here. That's the first part. And then we're going to solve the second part shortly. Alright. Now, how are we going to solve the first part? We can let the W equal to A plus IB, where the I square is equal to -1. It's an imaginary number. And then A and B are all real numbers. Now, this is our conditions that we need to set before we start solving this. All we need to do is just substitute this into this equation here. IW equal to this. It means IA plus IB is equal to 2 minus 2I squared here. Right. Now all we need to do is just expand the right hand side and then do a bit of modifications on the left hand side. Now we will get a negative B plus IA on the left, and then on the right we just need to expand it as usual. So this is 4 minus 8i, but the last one we have to be very careful. It's actually 4i squared. As I mentioned before, I squared is negative 1, and then that would actually give us a very nice result. That is 8i. Now because it is 8i, and then we know automatically a must be equal to negative 8 by comparing the imaginary component. And then for the real component, because there is no real sections present, therefore b must be equal to 0 there. And then there you have it. We can conclude that the solution to the first complex equation is w equal to negative 8. Is it negative 8? Yeah, negative 8 only. So that is a b there. Right? So that is the complex number solutions to this particular equation. I hope that is clear. I'm going to move on to the second one shortly. Alright, for second part, we need to sketch an Argand diagram showing the region R consisting of points representing the complex number Z as follow here. Now, we need to recognize this complex inequality, right, as a locus or a region of points that is found inside a circle that is centered at 4, 4, and then radius 2. Right now, in order to do this accurately and then safely in the exam, I would advise you to rewrite this form in this way. So we're going to factorize this. So there it looks something like this. The main reason why I want you to factorize this as a reminder that this is actually a circle. For this section, it represents a circle center, I would say centered at 4, 4. You can see that once you factorize that, you will write that as center as 4, 4 instead of writing negative 4, negative 4. Center at 4, 4 with radius of 2 unit. Yeah. But because this is an inequality, so there must be a region that is actually found inside that circle there. Right. Now I'm going to show you very briefly. This is a very simple task here. We have all we need to do is just draw the axis, imaginary, real. Right, this is the origin. Now there's around 4, 4 there, so roughly 1, 2, 3, 4 here. 1, 2, 3, 4. All right. Okay, from here we're going to mark down the coordinates. It should be around here, for instance. And then it has, oops, just let me correct my axis a little bit. I think I changed the scale a bit so that it's easier for me to relate to this. So let's start from 2, 4, 6, 8 here. 2, 4, 6, 8. Therefore, the center of the circle is around here, which is somewhere here. And then it has a radius of 2. So radius of 2 should be somewhere here. It will pass through this part here. Let me see, the radius is 2. And then This radius is also 2, and then it pass through 2, 2, 2, and 2 here. So let me see here. This, oops, sorry, hold on. Should be around here. Therefore, the circle will look something like this. Okay, and then there you have it. This is a circle centered somewhere here. All right, please forgive me for the accuracy here, but roughly the circle will look something like this. Centered at 4, 4, radius of 2 unit. So 2 unit around here. Okay, and then there you have it. But because this is inequality, don't forget we need to shade the region. So the region will be somewhere here. All right, and then there you go. That is the region represented by that complex inequality. Right, now I hope that is clear. I'm going to move on to the next sections shortly. All right, let's take a look at the second part of question B now. I have prepared a diagram to illustrate what does the question B actually represent. Let's read it through first. For the complex number represented by points in the region R here, given by this circle, which is indicated by this circle here, centered at 4, 4 here, that has a radius of 2. It is given that the complex number, the modulus of the complex number lie between P and Q. What that actually tell us is the magnitude of the complex number has a maximum value of Q and then has a minimum value of P there. So how does it look like over here then? Okay, it simply means that the the distance, the shortest and the longest distance from the origin. Okay, because we are looking at generally something like this. I'm going to show it to you what this actually mean visually. So we have our circle here centered at 4, 4. Now for the z, for the complex number z, we know that complex number z is represented in general as IB here. And then it actually represents a circle. You can visualize it as a circle with a specific radius. So take for instance, this could be the radius, or this could be the radius, or it could be somewhere here, for instance. This could be the radius, right? So if you are looking at the largest circle that you are looking at right now, this outline here, now that distance from the origin until here is the value p itself. That's the minimum value of radius of this circle z, which is represented by p here. So I hope that is clear here. And then it must be intersecting. The circle that I have drawn in dotted line must be intersecting with the circle that is given here, because the solution need to be found in the region itself. Right? So that will be the shortest distance for this radius of the circle represented by complex number z here. And then that would be our shortest distance for the magnitude of complex number z. And then we can further extend the circle here so that it looks something like this. The largest that we can have. Now by having that, right, we are looking at the maximum distance or the longest distance from the origin here until it touches the circumference here. Right, now my drawing is not that clear here, therefore I'm going to represent it using this drawing here, which is set up by GeoGebra. It's much more specific and accurate. Now you can see that this is the origin. The shortest distance, which is represented by P, is given by this distance here, from here to here. Right, so that will be the shortest distance. And then the longest distance, which is represented by the maximum value Q. Q is basically here. All right, so that will be our Q. All right, so that is the visual idea behind that particular inequality. I hope that is clear. Once you get that visual representations of this inequality, then we can solve it quite easily. All right, let me clear all this here, and then we can start to solve that. Okay, let me do this very quickly here. Okay, and then I'm going to we're going to start off by finding the shortest distance P first. We can find out the shortest distance P. How do we find the shortest distance P here? It's also quite direct. I would say that we can take the distance here. All right, I did not draw very accurately here. So we can take the distance from O to the center of the circle. All right, now let me clear this P first so that it's not very distracting for us. Okay, and then we are interested to find the value for P, which is given by this distance here. All right, to do that, we are going to find the distance from O here until the center of this circle. So I'm going to label that as C. The distance OC can be obtained quite easily. Distance OC is basically just because the C here is 4, comma 4 here. Therefore, the distance would be 4 square by 4 square here, square root. And that would give us 4 root 2. Now, that is the distance from O to C. To find the shortest distance P, therefore, we can conclude that P is basically 4 sub 2, subtract off with the radius of this circle. So we know the radius of this circle is 2 unit long. Here, you can see that. Therefore, we're going to subtract that. And then there you go. That's the value for P there. I hope that is clear. Now, next, using the same idea, we are going to find the longest distance from O until here. So I'm going to call that OP then. All right, we are going to find the longest distance. Okay, maybe I call that OQ then, because this one is Q, so I'll call that OQ here. This is P. So now the longest distance will be Q. How do I find the Q? You can see that very clearly from the diagram. OQ, OQ is just, you can either make use of OP or you can make use of OC then. OQ is OC plus the radius of the circle. And then that would actually give us 4 sub 2 plus a 2 there. And then there you have it. Those are the two values of P and Q that satisfy this inequality. And then the P and Q must be found in the region of R there. Okay, I hope that is clear. Now, next we're going to move on to find the argument. All right, so I'm going to show you the argument shortly. Right, next we're going to answer the second part of this, which satisfy the inequality for the argument. What that actually look like, I have already drawn the same diagram here. You can see the blue straight line. Now, the first blue straight line below here actually represent the line that produce the argument that is greater than alpha here. What I mean is this angle here is the alpha itself. Right? Now that will be the argument of the complex number z that is considered as the minimum angle where this line touches the circle here. And then the angle measured counterclockwise from the x-axis is known as the argument here. And then that is the minimum angle that we can have that satisfy the region R here. And then we can also have another tangent line that is touching the circle at this point here. And then this would actually give us the other argument. That argument will be maximum argument, which is labeled as beta here. All right, now that is the visual understanding of this inequality. And then how are we going to solve this? Okay, in order to solve this, we are going to make use of whatever positions that we know of from the circle itself, especially the center, right? So first of all, the first part will be here. I'm going to draw a straight line down here. And then first of all, let me clean up all this. We are interested to find the alpha, which is this one here. In order to do that, we are going to make use of this angle here. We're going to call that theta. And then theta subtract off with another angle here, beta, for instance. Oh, I shouldn't call it beta because they already have beta there. I will, oh yeah, I would actually call that like gamma. Okay, so I'm going to make use of the angle gamma here. And then by subtracting that with the angle theta, I will be able to obtain alpha. So here I'm going to say that alpha is basically theta, okay, subtract off gamma. That is how we obtain the alpha itself. All right. Now, first of all, uh, the theta itself can be obtained quite easily because we know that this is again is 4 unit long, and then the run is also 4 unit long. Therefore, um, I would say it's very clear that the theta is 45 degree then, right? So from there, we can conclude that the theta is 45 degree. I'm going to write down in terms of radian measure, so that it will be 45 degree. Now, the only concern now is the gamma. How do we find the gamma? We're going to draw another line here because the blue line is a tangent. And then we know the radius for this circle is 2 unit long from here. Therefore, we will be able to obtain the gamma quite easily. We know that tangent, or in this case, we can't use tangent anyway. We know the length for OC here just now. We have already obtained the length for OC, which is 4 sub 2. That's the length for OC. And then we can make use of one of the trigonometry ratio to find out the angle gamma. In our case, it will be sine gamma is equal to 2 divided by the length for OC. That will be this. Okay, so if we try to simplify this and then rationalize that, we will get something like this. This is 2, so that will be 1 over, oh sorry, not 1 over 4, it's sub 2 over 4. So it's sub 2 over 4 here, right? And then finally, we can work out the gamma as the sine inverse sub 2 over 4, right? And then by substitute this angle in radian measure, we will be able to conclude the alpha as pi over 4 minus of the sine inverse over here. Right. Now, if you like to leave it as it is, you can. But because the question say three significant figures, then so therefore we have to work out the actual angle in this case. All right. So let's give that a try. Let me try using my calculator here. I'm going to get that as 2 divided by 4 here. And then, of course, I need to convert that to radian measure for 8. All right, I will get this as some decimal number, of course. You can key into your calculator. And then after that, we need to subtract that by this number here, pi over 4. And then we will get, from my calculator, is that there's 0.424 here, radian, to the nearest three significant figures. Okay, now I hope that that is clear for the first alpha here. And then as for the beta itself, sorry, as for the beta itself, it shouldn't be a problem because this angle here is also the same as gamma. And in order to get the beta, we know that beta is all the way from the horizontal line until here. This is beta. So in order to get the beta, all we need to do is just take, well, it's up to you actually. You can either take alpha plus 2 gamma, or you can take theta plus the gamma itself. So beta is actually theta plus gamma. We know that theta is pi over 4, and then we just need to add up with the sine inverse sec 2 over 4 there. And then from there, we are good to go here. All right, so I'm going to pause here. I'm going to work out the answer that we have here. All right, so let me work that out one more time. Okay, that is divided by 4 here. Okay, and then I will need to, all right, so that is the one that I have currently. And then what I have is, okay, hold on, there's something wrong with my computation. Let me try to compute that one more round. Okay, I think you guys can try out on your own. Shouldn't be a problem at this point. Okay, that is, let me check my number one more time in case I make a mistake here. It's always good to check in the exam. Okay, so now I got what I need, and then after that, finally, I need to conclude my answer as 1.15 here to the nearest three significant figures. Of course, you guys can always check my numbers here in case I make a mistake. If there's a mistake there, just drop your message into um, the comment section. Yeah, and then the rest can pick up from there. Right. So I hope this is clear for this question. I'm going to proceed on to the next question requested by the students. Right. Right, here is another question requested by the students for clarification. I still remember this question has been requested by multiple students before this. Okay, so I find that this question is good for discussion here. All right, we can read through. The complex number z is defined as, in its general format, z equal to a plus ib, or in its rectangular form, where a and b are real numbers. The complex conjugate of z is denoted as z star. Show that, the first one, show that the square of the magnitude can be written as the product of the complex number and its conjugate. That's the first one we need to prove. Then the second one, we need to prove that the complex conjugate for z minus ki can be written as the complex conjugate z star plus ki here, where k is real. All right, now let's start with this. Okay, now we know that the z is represented as a plus ib. That should not be any problem there. So a plus ib is the z itself. This is a complex number. Uh, this z square, okay, z square, I would actually do it this way. I would say z square like this, and then I would say that a lot of students would in the exam they would actually do something like this. All right, you would go ahead and do this in the exam, most probably. All right, this one is actually plus b square I square, and then just as a reminder, because this is a complex number, therefore the I square itself is given as -1. Okay, therefore this one can be simplified as a squared plus 2abi minus b squared. Yeah, this is what um, some students will actually do this after a long time. Right? Now, if you do this, right, this is entirely, I would say, does not fit in the definition of the square of the magnitude of z. What that actually mean by this symbol is something like this. So you need to be very clear here. if I were to draw out the Argand diagram, this is a complex number that has um, that is like A unit to the right and then B unit up. So the complex number should be somewhere here. The Z magnitude or the magnitude of Z, right, basically means what is the distance from O here until the tip of this complex number. What is the magnitude of this line actually? So the magnitude of this line is typically, we know is A unit over here and then B unit up here. Therefore, the magnitude of Z is given by Pythagoras theorem, A square plus B square square root. Therefore, for Z square, it simply means A square plus B square. And then it's not, and then we should not be doing algebraic expansion for this, for complex number especially. So this is one reminder I need my students to know for this. Do not commit these wrong definitions of the square of the magnitude of complex number. It should basically just means distance measured from the origin. Right. So once you understand the definition, and then we can attempt the question. Right? Because you can attempt these questions with all the algebraic skill or knowledge that you can have. But at the end of the day, it may not make sense to us. Right? So this is where the definitions come in to help to clear the cloud. All right? Okay. So let's start all over again. Right? I hope that is clear now. Since you know that is typically the distance, therefore we can conclude that z square, the magnitude of the square of complex number, is basically given by a square plus b square. It simply means it's the distance measured from the origin there. Okay, so make sure we know this. And then next we have already proven the left hand side. This is our left hand side. In order to prove that the left hand side is the same as right hand side, now we're going to sort of compute the products of z and its complex conjugate. So z and its complex conjugate. The z is a plus ib here. And then the complex conjugate is always written as a minus ib. And then with a bit of expansion, yes, this one you can expand because this we don't define this as a magnitude yet, right? But when we see this, we know that it represents magnitude. So therefore, we can actually carry out the normal algebraic expansion. We will get a square. Of course, this is a plus b, a minus b form. Therefore, you can simplify it as a minus ib square. And then with a bit of simplification, you will find that this is a square minus I square b square. And then I want to remind you again, I square is negative 1. So I square is negative 1. Therefore, this one must be equal to a plus b squared. And then guess what? This is exactly the same as the square of the magnitude of c. And then there you have it. We have provide a proof for the first part. I hope that is clear. All right. Next, I'm going to clean up, and then we're going to move on to the second part here. So let me clean all this up. So the second part is to prove that z minus k conjugate is equal to this. All right. Now let's give it a try then. On the left hand side itself, we have z minus ki conjugate. What that actually means is we have to turn the expression inside the bracket to become the rectangular form of a complex number that we can recognize. Right? We cannot simply write this as, bear in mind, do not write z plus ki like this. That does not signify the complex conjugate of this entire complex number because the z is another complex number which is written as a plus ib. So therefore, I need to clarify here, do not write something like this, but instead, we should replace the z with a plus ib here, minus ki. And then from here, you can do a bit of rearrangement. Like terms, group them together. Of course, here we have two imaginary component, which is b minus ki here. And then conjugate that. Now we can apply the complex conjugate. That will be a minus, because complex conjugate, if you have z as a plus ib, the complex conjugate will be a minus ib. And then we're going to apply the same idea here. There will be a minus bki here. Or sometime you can rearrange this again. Of course, you can rewrite as a plus k minus bi like this. And then, or you can reattach, sort of separate the k and b out. In this case, it will be a minus bi plus a ki. And then you notice that I have written down here, this a minus ib or bi here represent the complex conjugate. Therefore, this entire thing is the complex conjugate z. So therefore, z plus ki. And then there you have it. We know that left hand side actually represents z minus ki complex conjugate, which I have written down here. Therefore, we have therefore we can conclude that z minus ki complex conjugate is the same as z complex conjugate plus ki. And then it is proven. Right? So I hope that is clear for the first section. We're going to move on to the second section shortly. Alright, next let's look at the second section of this. In an Argand diagram, a set of points representing complex number z is defined by this equation here. Right? Now, by squaring both sides, we need to show that or prove that this equation is equal to 0. And then thereafter, we are going to show that this entire complex equation can be simplified into this form. And then lastly, based on this form, we're going to describe the locus represented by this complex equation. All right, let's get started with this. First of all, we're going to refer to the complex modulus here. We're going to square both sides, both of these. Okay, square both of these. Right. By squaring this, it will look like 4z minus 4i, the square of the modulus. As I mentioned before, do not go and expand it. That's the reminder for those who are sitting for the exam soon. What you need to do is make use of all the result that we have obtained previously. Like if you want to obtain the square of the magnitude, we should be using this one here. By that, it means the z and the complex conjugate of the complex number here. All right. So what that actually mean is z minus 10i. This basically represented by this. So it's the product of the complex number here with its own complex conjugate. And then that would give us the square of the magnitude of the complex number. All right. And then we're going to proceed on the same goal for the right hand side expression. There will be 4z minus 4i with z minus 4i complex conjugate. Okay, that's how it would actually look like. And then next, we're going to make use of the second result here. You can see that z minus ki conjugate can be written as this. Therefore, it will become 10i. This can be written in this form, which is z complex conjugate plus k plus 10i here. Now the same go for this one, z minus 4i, z complex conjugate plus 4i. All right. And then from here we just from here you can expand. Yeah, by all means, if you are too desperate to expand, this is the right time for you to expand now. We will get a z and here, and then of course you will get a tan zi minus a tan z complex conjugate I, and then finally we have minus 100 I square. That is 100. And then that go the same for the this one here. I'm going to expand it directly with the 4 itself. So there will be 4z star here. And then after that, I will have my 16zi. And then I will have my 16z star or complex conjugate I. And then finally, I will have my plus 64 because there are 4 of them. Plus 64 here. And then right after this, you guys know what you need to do. It's just to simplify the like terms. I'm going to bring everything to the right hand side, maybe because it is the right side to get the right answer. Huh? Okay, so from here we will get z star, and then combine with this, we will get the z here, which is a 6. Did I get it correctly? Let me see here. We have 10z, yep, correct. This is a 4, let me see, 4 for 16 there. Yep, that's correct. Therefore, I'm going to move over there. That will be plus 6zi. And then the same thing here, there will be 6z complex conjugate I. And then finally, I will have my negative 36 equal to 0. And then simplifying everything here by 3. And then I'm going to check whether I got the right answer. Okay, if I want to get exactly the same, I might want to do a bit of rearrangement. Actually, this is already considered as a correct answer. Now I'm going to just rearrange so that it match the question itself, but you don't have to do this in the exam anyway. Okay, so basically it looks something like this. Minus a 12 equals to 0. And then there you have it. It has been proven that by squaring both sides, we can actually obtain this complex and complex conjugate equation here. All right, so I hope that is clear. I'm going to pause here for a while. Later on, I'm going to show you how we can restructure and factorize this complex conjugates equation so that we can describe it in this form that we can describe the locus easily. All right, next. We are still on number 2. We have managed to prove that this is true. And then next, we're going to restructure and factorize this complex conjugate equation so that we can describe it in its simplest form that will allow us to describe the locus more easily. Okay, now we're going to start from here. I'm going to just rewrite the equations one more time. Right, this is my first attempt. In the exam, usually quite nervous, all right? So assuming that I'm actually sitting for the exam right now, I will have this first attempt, all right? Because we may not be able to get it right in the first place, right? So by looking at my first attempt, I might have this kind of idea that looks something like this. I noticed that, all right, there is some sorts of factor going on. All right, so I can try this. I can try to regroup this. This z here, sorry, negative 2i z star minus a 2. Right, and then I notice that the z can be factorized, so therefore I'm going to factorize that. You must be wondering at this point of time, why would I think of factorizing the z instead of the z complex conjugate then? Now, of course, by all means, you can always factorize the complex conjugate z. But the thing is that the main reason why I want to factorize the z out because I noticed that I can make use of this. If you are able to factorize it out in this form, then we can rewrite this in this form. Now that is my motivations behind as to why I would rather factorize the z out instead of factorizing the complex conjugate z in this case. Right. Now once I have found out this, and then I'll try to make some sense for my next two terms then. I might have this idea. I noticed that, all right, there's some sort of a factor going on also. I would like to rewrite like divide and conquer because that's my favorite strategy. I will always try my best to divide and conquer it, like 12. 12 can be written like 4 and 8, for instance. Yeah. And then from here, I can factorize. Okay, let's leave this out for a moment. I'm not going to write down. I'm just going to show you this term here. I'll try to factorize it this way. I'll take out 2i, and then I have my z complex conjugate, which I can make use of this later on. That's my intention. And then I'll try my best, like how can I make it a 4 then after I multiply with 2i. So I have an idea saying that, all right, it could be 2i. It could be 2i because 2i multiplied with 2i, it is negative 4. But with the present of negative, I might have to put a negative here. If I put a negative, and then once I expanded this, right, I do get a negative 4. I'm quite happy with that. And then this 8 here, I can actually move it to the other side. That become an 8. And then now I'm going to rearrange everything back. This is my first attempt. It's considered as quite good already. Yeah. And then right after this, I can actually convert this. I notice that this is plus, I can convert it here. But the poor thing here is I don't have a plus on my next term. So therefore, it's very hard for me to proceed on here onwards. Right? So I'm going to stop my attempt at this point. But of course, some of you have a lot of crazy idea that you want to try out. By all means, you can drop your idea in the comment section. All right. But for me, at this point, I noticed that if I can't make use of all the section that have been given to me, I would rather ditch this method, and then I'll try my best to restructure it again. Okay. My second attempt. I'm going to erase all this where they are a bit of stumbling block for me at this point. And then I can sort of agree up to this point is quite a good start when I rearrange it, when I restructure it this way. It's quite a good start because I managed to get the z complex conjugate with the 2i down here. This is a good start. The only difficulty that I have is this part here. This part, this is my second attempt now. This part. How can I make this so that I can make use of the plus instead? All right. So instead of divide and conquer, you now I can't divide and conquer. That strategy may not work nicely. So therefore, I need to get help. Get help generally means you introduce a new number into. So that's how we get help. Right? So one way we can reintroduce the number will be something like this. The number that you introduce, yes, you can introduce many different number, but we want to make sure that number can help us to reach certain conclusions that we need. And then that idea could be something like this. I need a negative 4 here for sure. I need a negative 4 so that I can factorize it nicely. And then to have a negative 4 here, how can I get my negative 12? So I have that idea of, oh sorry, not negative 4, plus, you can say that initial idea I could have a negative 4 there. Just like what I did, right? I accidentally repeated my first attempt. So negative 4 and negative 8, all right? Now that doesn't work, so I'm going to ditch that method. I'm going to introduce plus instead, plus 4. Plus 4 will work because minus 4, I can't get the form that I want. Now I'm going to change it to plus 4. And then how do I get negative 12 then? So I have to introduce negative 16. This is the help that I need to get. If you can't divide and conquer, get help. Right? This is the help that we need. And then now, second attempt, I'm going to try to factorize one more time. Let's see whether it's a successful attempt or not. I'm going to take out 2i, z complex conjugate. This one will be plus. I try my best to put in plus 2i. I need to check also at the same time. If I expand that, I'll get negative 4i squared. Negative 4i squared, which is actually a plus 4. All right, I'm very happy with that. And then this 16, as I mentioned before, I can actually move it to the other side. And then, to my surprise, I noticed that both of them have the same factor. I didn't realize that until I actually write it down, right? This is what happened in the actual setting. So I'm going to factorize the z complex conjugate plus the 2i. By factorizing that, I will end up here. Because z complex conjugate plus 2i, I can factorize it like this. And then the z complex conjugate plus ki can be written in this form. Therefore, z2i, z minus 2i complex conjugate is equal to 16. And then we know that from the first proof, the product of complex number and its complex conjugate would give us the square of the magnitude of the complex number, which means this is the square of this. And then by square root both sides, we will end up with a 4. All right, and then that is how we can prove that from this complex conjugate equation, we can arrive to this simplest form. Now we write down it has been proven. All right, so I hope that is clear here. Some of you might be wondering, should I write plus or minus? Actually, when you put the absolute sign, it basically means plus or minus, so you don't really need to explicitly put the plus or minus. All right, so that is the proof for this one. I hope that is clear. And then lastly, for number 3, describing the set of points geometrically. This z minus 2i modulus equal to 4 basically represent, you can say that it represent, if I were to show the actual Argand diagram, this is actually negative 2 here with the radius 4. So the circle is actually a circle, right? Let's hope that I can draw it as accurate as possible. Please forgive me on this. Right, this is the center of the circle. The center is at negative 0, negative 2 here. All right. Now, to describe the points geometrically, we say that this complex equation represent a locus of a circle centered at 0, negative 2, and let me check. Now you can see that in the exam, when I look at this number here, I accidentally make a mistake myself. You see that when I copy negative 2, I thought that the center of the circle is actually at negative 2, but that is not true. Now you can see that this is also a reminder, a reminder not to commit this mistake here. Now, how do we avoid this mistake? We should avoid it this way. Let me erase it off. To avoid this mistake, don't get too excited. First of all, you must re-describe this, factorize it as much as possible. Put a bracket here. That is actually 0 minus, sorry, 0 plus 2i. Sorry. Okay. Now that actually looks something like this. Always introduce the bracket there. As a reminder, this is the center of the circle. Instead of just read that directly off, you may accidentally read the negative sign also, whereby we should not read the negative sign. It should be 0, 2. Therefore, I'm going to redraw this Argand diagram one more time. Read here, real, and then this is the imaginary. Now, the center of the circle should be at 0, 2 instead of 0, negative 2. And then the circle will be something like this. I did not draw correctly, but roughly it represents a circle. So to describe this geometrically, this complex equation represents a locus of a circle centered at 0, 2 with a radius 4 unit long, with a radius of 4 unit long here. All right, so I hope that is clear. It's a circle. It's not the region inside the circle, but it actually represents the outline of the circle, which is the circle itself. Right. So I hope that is clear up to this point. We're going to move on to the next question shortly. Right, let's take a look at the next requested question here. This is a much more simple version, but I will show it to you how to work out this solution here. We have the complex number is given as 1 minus I, denoted by U. Showing all your working without using calculator, express this complex number in the form of x plus iy, where x and y are real. Okay, let's start with the first one, which is quite easy to get. There are two strategies we can work with this. Okay, now we are given u equal to 1 minus I here. All right, now I'm going to show you three strategies there. First one is by first two are using algebraic approach. Then the third one, I'm going to show you how to use Euler methods to find the rectangular form of this ratio of these two complex number. Right? Let's start with the easiest one that most of you would use. Okay, is rationalization. Because u is equal to 1 minus I, therefore I over u is basically I over 1 minus I. Yes, we are going to rationalize it because that's what we have been taught all this while. Rationalize it using its complex conjugate. Okay, that's what we have. And then with a bit of simplification, even though it says without using calculator, well, I think at some point you can actually key in into your calculator, right? That's the purpose of the calculator anyway, and including this. Like myself here, if I don't use calculator, I'll just have to do it manually in this case. We will have I plus I square over this. You can use the a square minus b square formula. That will give us a 1 square minus I square. And then eventually we have, this is negative 1, so I'm going to write down negative 1 plus I. And then this one here is negative 1. A reminder again, I square is equal to negative 1. Therefore, that will be a 2. Then, because they want it to be written in this form, then we can conclude that I over u can be written as negative 1 over 2 plus 1 over 2I there. And then there you have it. That is the solutions to this ratio of the complex number. I hope that is clear. That's first strategy. Then the second strategy. All right, now let me erase this off. This is the first strategy that we always use. Then the second strategy. You can also apply this sometime in certain situation. It might be much more useful and more direct approach, right? Which is still algebraic. We will let I over u is equal to x plus iy, because they want us to write this in this form. Therefore, we will just say that, all right, can I just let this equal to this form then? Right? Now, knowing that u is given as this, I just rewrite that one more time. Now, all I need to do is just solve this algebraically. Now, solve for the x and y. I can multiply both sides by 1 minus I. That will give me 1 minus I here. And then with a bit of algebraic expansion, I'll have xi plus yi, and then finally minus I square become plus. So I just write it down like this, and then collect or combine the like term, the real component together, and then the imaginary component together. All right, and then on our left hand side we only have imaginary number. Therefore, by comparison, we can conclude that x plus y must be equal to 0, because there is no real parts here. There's only imaginary part, which is given as a 1. Okay, and then you know the next move from here is to solve this simultaneously. That is quite easy. I can take 1 with 2 here to eliminate the x. Therefore, my y will be a half. And then all I need to do is just substitute my y into either one of these. Let's assume that from 1, I think that's the easiest to have, x will be equal to negative half. And then therefore, to conclude that, we say that I divided by u can be written as x. What is my x? My x is half, and then plus my half I. And then there you have it. It's exactly the same answer as what we got from rationalization. All right, so I hope that is clear. And then lastly, I'm going to show you how you can make use of Euler form to answer this question here. Let me clean this up here. The third approach is by using Euler. Now, if you are not very familiar with Euler, um, do not use it. Only if you are familiar with this, then only you should use it. Right? Now, for Euler, the best the startup is to sketch out the Argand diagram and then recognize its magnitude and argument, because the magnitude and argument embody the entire complex number. So, take for instance, for u, I'm going to draw the Argand diagram that represent the complex number u. That basically means it's 1 unit to the right and then 1 unit down here. That is my complex number u. Okay, it's 1 unit down, 1 unit here. Okay, and then the argument for this complex number is, I'm going to label it as theta here. Okay, the magnitude of this, magnitude of u is equal to the Pythagoras theorem. You will notice that that is just a cert2 because it's 1 unit long. And then the angle theta, I don't really need to tell you how you can work it out, because it's 1 unit to the right, 1 unit down. That angle divide this 90-degree equally. That must be 45 degree. Then again, for some of you who like to really find out, you can actually use tangent theta. Tangent theta is 1 over 1, then, which would yield theta equal to pi over 4. But you can write theta equal to pi over 4. But when you write argument u, you cannot write pi over 4, because the way we measure the angle is clockwise in this case. Therefore, the argument should be written as negative pi over 4. That's one thing we really need to remind ourselves of. Argument is argument. Angle, yes, it is pi over 4, but argument is measured clockwise, negative pi over 4. Now, why do we need this? We need this so that we can describe the u in its Euler form. Now we know that its rectangular form is this. Its Euler form is written as r, the magnitude, is written as the magnitude, e, I, the argument of u. That is the general format for any complex number in the Euler form. Now the magnitude of u is cert2, e, I, and then the argument, we know the argument is negative pi over 4. And then there you have it. You can leave it as it is. That is our u in Euler form. And then the same thing go for I. I is pretty straightforward. I is just one, there's no moving left or right, but it's just 1 unit up here. This is imaginary, and then this is real part. And then I is just 1 unit up. The argument is very obvious. It's pi over 2. Therefore, the length itself is also, the magnitude of that I is also 1 unit. Therefore, I can be written in its Euler form as 1 unit long exponential I, because its argument is pi over 2. So therefore, we can write pi over 2 here. Now, next, once we have done this, we are going to simplify this. I divided by u can be written as I is ei pi over 2 over e, so it's cert2, because u is written as cert2 e I negative pi over 4. And then once you have written everything in its Euler form, we can make use of the index rule. So from this index rule, we found that we have 1 over 2 exponential pi over 2 plus this. That would actually give us 3 pi over 4. Okay, I hope that is clear at this point. Now that is actually the answer if we wish to leave it as Euler form. But they want us to convert it back to rectangular form. How can we convert this back to rectangular form? We can convert it back this way. This entire thing can be written as square root of 2. The Euler format. Euler format is here. I'll try to write down as a reminder. Ei theta can be written as cos theta plus I sine theta here. And then here we can rewrite as cos 3 pi over 4 plus I sine 3 pi over 4. And then with the help of a calculator, you will notice that this is actually negative half plus this one here is a positive square root of 2i here. And then with a little bit of help of simplification, we will get negative half plus a half I there. Did we get the same answer? Let me check again. I sort of forgotten our answer previously. Okay, let me check this one more time here. That is 1 plus I is a 2. And then we have negative 1 plus a I over 2 here. So it's negative half plus a half I. Oh yeah, it is the correct answer. Now, there you have it. 3 strategy to answer the first part here. But bear in mind, Euler form is quite easy to use in our case because the angle measured is quite easy to recognize. There are times when the angle is not some spatial angle, then Euler form may not be that suitable when that happen. All right, so I hope that is clear. I'm going to move on to the second sections shortly. All right, let's continue on to second question here. On an Argand diagram, we are going to sketch the loci representing complex number z satisfying the equations given as below here, z minus u equal to the magnitude of z, and z minus I equal to 2 here. Now let's start with the first one. Now if you are not sure what sorts of loci that we are looking at, you can always use or convert the complex form into the Cartesian form. Take for instance, we can represent z as x plus iy here. And then we get to substitute this into the complex equation, which is this iy minus a u. And then we know that u is represented by this 1 minus I here, 1 minus I, is equal to the magnitude of z. And then we know that z is this. Okay. And then group the like term. We have x minus 1, the real component. And then we're going to group the imaginary components together. And then that looks to me like a y plus 1 I here. And then there you have it. This is what we have at this point. And then just a reminder again, the modulus symbol represents the distance measured from the origin. Therefore, we're going to apply the Pythagoras theorem here. It's x minus 1 square plus y minus 1 square equal to x square plus y square. Now, of course, originally there is the square root, but we can get rid of the square root by squaring both sides here. And then we have x minus 1 square plus y plus 1 square equal to x square plus y square. Now, if you try to expand this, you will notice that the x square and y square can be cancelled off. What is left is only negative 2x plus a 1 plus 2y plus a 1 equal to a 0. And then with a bit of simplification here, you found that is negative x plus a y plus a 1 is equal to 0. And then finally, we can simplify this as you can write down in term of y equal to mx plus c. So in term of y equal to mx plus c, it is written as here. I'm going to write it down as y equal to x minus 1. So it is actually just a straight line with a gradient of 1 and then passes through the y-intercept at negative 1. Now bear in mind, it is straight line with a gradient of 1 passes through the y-coordinate of negative 1 here. Okay. Now if you can visualize this, it will look something like this. I'm just going to draw a very simple representation of that loci. And then this is like 1 here. This is a negative 1 because it passes through negative 1. And then it has a gradient of 1. Excuse me. It has a gradient of 1. Therefore, this line must look something like this. Passes through a 1. It has a gradient of 1. You can see that very clearly. Okay, now that is y equal to x minus 1. And then we are done for the first loci. All right. Now, in terms of complex description, we say that this particular complex equation represent the perpendicular bisector between 2 points. What do I mean by perpendicular bisector between 2 points? This is what I mean by that, right? Let me rewrite this one more time. Is z minus u, your u is this, is equal to z minus 0 plus 0i. So I purposely write down like this just to show you that on the Cartesian plane, there is a point 0, 0, which is origin here. And then there's another point which is 1 and negative 1, which is here. This is a B here. And then we are trying to find the perpendicular bisector between these 2 points here. Okay, perpendicular bisector, to get perpendicular bisector, we must find the midpoint. We must find the midpoint between these two points here. Therefore, based on this, right, the midpoint here, midpoint M is basically given by, it is very obvious, you can check that directly, is 0.5 and negative 0.5, of course. Now that is the midpoint. And then next we need to draw a straight line that is perpendicular to this line OB and then passes through the midpoint. That is what we call as the perpendicular bisector between the 2 points O and B. That's how we describe this complex equations, locus or loci in this case. All right, so I hope that is clear. That's the first one. If you are not sure what you're looking at, then you can always convert that to Cartesian form so that you can plot the straight line. Of course, if you convert it to Cartesian form, we lose that descriptions of the perpendicular bisector. But if you rearrange the complex equation in this form, then yes, we will be able to describe the perpendicular bisector more explicitly. This one is more embedded in the Cartesian form, so it's very hard for us to really tell the or identify the description that we are looking at here. Okay, so I hope that is clear. That's the first one. Next, I'm going to erase off this working here. I'm going to show you the second one. The second one, of course, you've seen it like 1,000 times before if you have learned complex number before this. This is basically a circle that passes through the point 0, 1, and then it has a radius of 2. Okay. Now, if you wish to convert that to Cartesian form, so I'm going to walk you through one more time, just as a revision, but it's not required by this question anyway. Therefore, the same thing here. We know that z represents x plus iy, so we can substitute that. X plus iy minus I is equal to 2. Now, what I'm trying to show you here is how do we relate the complex equation in Cartesian form, all right? Which is not required here. It's just a recap. Now, the second step is to join or group the like terms together, the real component and the imaginary component. So we have x plus y minus 1i. And then a reminder again, the modulus represents the distance measured from the origin. That will give us this square root equal to 2. And then with a bit of simplification here, square both sides, we will get equal to 4. And then you will quickly recognize that this is the Cartesian equations that represent a circle with radius 4 units with at the center, I can say that, centered at 0, 1 here. Okay, centered at 0, 1. Now that is the loci or locus represented by this complex equation. Now I hope that is clear. All right. Now if I were to sketch it onto this graph here, onto this Argand diagram, it will look something like this. It's centered at 0, 1. So 0, 1 is around here. This is 0, 1 here. Center is over here. And then it has radius of, oops, sorry. I think I make another mistake here. So it's a good reminder. Since I make this mistake, I want to remind all of you that this 4 is not the radius. I accidentally saw this as a radius. You can see that once I remove the square root, I become a bit rude in this case. Let's try not to be rude here. Once you remove the square root, be gentle a bit. Remind yourself the radius is actually shown by this number, not the 4 here. Or sometimes it's best to write as 2 to the power 2, just as a reminder to indicate the radius as 2 instead of 4. That is a good error that I have made here. So it's actually a circle with a radius 2 units. Luckily, I saw this, right? Now, once we have done that, we can sort of visualize how the circle would actually look like. So if I were to roughly sketch this, okay, it is 2 unit. 2 units. So basically, starting from here, it should pass through here. It should pass through here, and then somehow it would look something like this. Okay, I did not draw properly here. Something like this. Something like this, centered here. So it's a circle and a perpendicular bisector straight line. And then they do intersect at these 2 points. Of course, we must know that it intersect at this point here because they do meet at -1 with a radius of 2. All right, so I hope that is clear at this point. Now, in order to visualize this more accurately, I prepared the drawing using GeoGebra so that we get a better view of the locus system. And then we can represent it on the Argand diagram. Now, let me show it to you how the Argand diagram actually look like. Okay. Now you can see that this is how the Argand diagram, that represent the loci for these two complex equations. The first one being the circle centered at 0, 1, and then the other one is perpendicular bisector of the point B and A here, or O and A, if you like. And then they do meet at this point -1, and there's another point uh, over here. Right? Now, the detail about where do they intersect is very important. We're going to look at that shortly in order to answer the following question. Find the argument of each of the complex number represented by the point and intersections of the two loci here. So I'm going to pause here. We're going to come back shortly. All right, now we're going to look at questions number 3 here. Find the argument of each of the complex numbers represented by the points or intersection of the two loci. Now, it's advisable in the exam to draw or use a compass and protractor to draw as accurate as possible so that you can visualize it more accurately, like how it looks like here. Right? The intersection is at these two positions here, point P, which is at that coordinate of 0, -1, and then there's another point here, Q. Right? Now, because the gradient of this line is 1, you will notice that it does pass through this point here. Right? And then the height of this point must be 1 unit because the gradient is 1 here. Okay, and then therefore this line is actually parallel to the x-axis. Right. Now, knowing that will give us more opportunity to solve these questions simply, I would say. All right, let's look at the first one, P. P is the easiest of all. We want to represent the complex number P first. How do I represent the complex number P, which is represented by this line here? Let's call this complex number as V then. Okay, now we know that this complex number V can be written as easily a 0, -I, like this, because it's 0 unit, -1 unit down. Or simply you can just write down -I here. Okay, its argument is an angle measured from the imaginary from the real axis. This is the real axis. This one here is the imaginary axis. Therefore, any angle, any argument that you need to find for complex number, it must be an angle measured from the real axis, either clockwise or counterclockwise. In this case, this complex number here, for this complex number, we have to measure it clockwise from the real axis, and then it's very obvious is 90 degree. Therefore, we can say the argument of V is 90 degree in radian measure. Right, now I hope that is clear. You can also represent this in the Euler form. So if you want to represent this as Euler, it has a magnitude of 1 unit. So 1 unit exponential I, and then is -pi/2. Oops, I forgot my negative. It's -pi/2. Its argument is -pi/2 because we measure it clockwise direction. All right, now that is the first answer. We have already found the argument for one of the complex number represented by the point or intersection P here. Now next we're going to find for Q, which should not be any problem here since we know that Q and D is sort of passes through this parallel line, and then we need to find out its argument, which is here. This complex number, let's call this complex number W then. Now we know complex number W is represented by 2 plus I. 2 plus I. And then the argument for this complex number can be represented by this angle measured from the real axis, clockwise in this case. Let's call this theta then. So this data clockwise. Clockwise is positive. And then how do we get this angle? That would be very straightforward. We know that this is 1 unit long. The run is 2 unit long. Therefore, we can take the inverse tangent 1 over 2 here. And then there you have it. If you want to leave this as it is, it's fine. Or you can key in into your calculator for this number here. So take for instance, if I key into my calculator, the question never say that it has to be in pi. Therefore, you can leave it in pi or decimal number to the nearest 3 significant figures. Usually that is a requirement. Let me try to find out from my calculator here. So I have like, I need to convert that to radian measure. Okay, let me convert that. Okay, so in terms of radian measure, right, this argument is 0.464 radian. Okay, and then there you go. We have found the argument for each one of the complex number that represent the intersections between the circle and the perpendicular bisector straight line. I hope that is clear. These are the two answers that we are looking for. Okay, and then of course, lastly, before we end, we can also represent this complex number in the Euler form. In terms of Euler representation, first of all, you have to find out the magnitude for this complex number W, which is a cert phi. And then therefore, in Euler form, the complex number W can be written as cert phi I. The radian is 0.464 here. Okay, now this is the complex number that represent the point of intersection Q here. And then this one here represent the intersections of the complex number at the position P here. All right, now that concludes our solutions to number 3. I hope that is clear. We're going to move on to the last complex question requested today. All right, stay tuned. All right, here come our last question requested by the students. This question is much more easier than all the questions that we've done so far. I'll just walk you through again, and then do remind yourself all the precautions that you need to take whenever you handle complex number, especially first rule of thumb. I square must represent -1 here. Okay, and then don't forget the modulus of z represent distance. Remind yourself that actually is a distance measured from the origin. Okay. Now the first question, without using calculator and showing your working, express u in the form here. Now there are many ways to do it. One way you can use Euler form. Now for this example, the argument for the complex number may not be some spatial angle. So I will advise you to use the normal methods, rationalize it, or by using the algebraic methods. Okay, now I'm going to show you both again one more time. So the first one is to rationalize it. We're going to use rationalization. First of all, we're going to expand this, of course. If you expand that, there will be like 4i. And then be very careful with the last one, as I mentioned before. That is actually a 4i squared divided by 2 plus I. And then we're going to simplify that. That is a -3 plus a 4i divided by 2 plus I. And then using the rationalization method, we are going to use its complex conjugate for the denominator. That will look something like this. And then the denominator will be 2 plus I, 2 minus I here. And then that will give us this is -4i squared. So that would actually give us a 4. Right? It's a -4i squared, so that is a 4 itself. And then denominator shouldn't be a problem. If you expand this, or by using the a squared minus b squared formula, we will end up with 4 minus I squared. That's the one thing you need to remind yourself of. And then after that, simplifying the numerator, we will get negative 2 plus 11i divided by a 5 here. And then therefore, we can conclude that the complex number u can be written as negative 2 over 5 plus 11 over 5i. Okay, now that's we have already shown that the u can be written in the rectangular form x plus iy as required by the question, where the x and y are all real numbers. All right, now I hope that is clear. The second method is very similar to the first method, but we don't actually use rationalization here. We're going to start off from this section. So this is strategy number 1. Strategy number 2, you can, or method number 2, you can straight away start from here. You still need to carry out this step here, expansion. And then once you're done that, you are going to let this 4i be, so let this be x plus I y. And then performing a bit of algebraic expansion. So we're going to multiply both sides by 2 plus I. Then that will give us this. Okay, and then by expanding this, we get 2x plus 2yi plus xi minus a y. I straight away convert that, and then group the like terms, the real components together, and then group the imaginary one together. We have 2yi here. And then I'm going to write this side by side. By comparing the real component with the real component between the left and the right expression, and then compare the compare the imaginary component with the imaginary component here, we will be able to obtain a simultaneous equation. Here you will see that the simultaneous equations would look something like this. 2x minus y is equal to negative 3. That's our first equation. Then our second one will be x plus 2y equal to a 4. And then we can solve this. Once you solve this, you will be able to find out the x and y here. Okay, now in this case, the solutions to the simultaneous equation, I will leave it to you. I think that will be a piece of cheesecake for most of you. If you solve this, hopefully we pray very hard that your x would end up with 2 over 5, and then the y would be 11 over 5. Therefore, from here, we can conclude that the u can be written in the rectangular form x plus iy there. Okay, now before we move on to the second one, just let me quickly check through if that is correct or not. All right, now let me remove this section here. I'm just going to do a bit of checking here on this. So if I were to multiply 2 both sides, I will get 4x minus 2y here minus 6, and then we have x plus 2y equal to a 4. That is our third equation, and then this is our second equation. So if we were to eliminate that, we have 2 plus 3, we have 5x is equal to negative 2. Therefore, x is equal to negative 2 over 5, which is correct. And then after that, we're going to substitute it here, or we can substitute it back into 1. From 1 itself, we will get like the y is actually negative 4 over 5. Okay, negative 4 over 5 plus 3, which is 11 over 5, which is here. Right, now by checking through, we did find out that our answer does match with the rationalization method. So I hope that is clear for this. We're going to move on to the second question shortly. All right, let's take a look at the last section here. This is sort of like a recap. We have done one of these questions in the previous questions before. here I'm going to rewrite this one more time. It is represented as z minus u magnitude, and then the magnitude of u. Now just to recap, the magnitude of u is negative 2 over 5 plus 11 over 5i here. Okay, so from here we can substitute this one into here. That u is written as 2 over 5 plus 11 over 5i here. Bracket. Okay, and then the magnitude of u. Okay, this is the magnitude of u. I just rewrite this one more time. So you must remind yourself that this is the magnitude of u itself. So what is the magnitude here? Magnitude is given by negative 2 over 5, or just 2 over 5 square here, plus 11 over 5 square. And then it is the square root, just as a reminder. So if I were to simplify this, let me see, 1 to 1, 1 to 5. Okay, so this one is 1 to 1, and then with a 4 is 1 to 5 here. That will give us 25. So after we simplify, it's 25, and then therefore it's just 5. The magnitude is 5. Okay, and then we can simplify this further. That can be written as negative 2 over 5 plus 11 over 5i here, equal to 5. Now, this format represents the locus of a circle centered at this point here, and this circle has a radius of 5 units here. All right, so I'm going to describe that at the side. This is a circle, so the locus is a circle of radius 5 units, center at negative 2, 5, and 11, 5 here. All right. So I hope that is clear. Very obvious. You can just sketch it out on your own. So I'm going to roughly sketch here. This is not a very accurate scale here. Imaginary axis and then the real axis. All right. Now it's a negative 0.4 unit to the left, and then 2.2 unit up here. So somewhere here, this is the center. I just roughly represent this as negative 2 over 5. This part here is 11 over 5 here. This is the center of the circle. It has a radius of 5 units here. So I just roughly sketch here because it's not very accurate here. Generally, it will look something like this. So the center of the circle is over here. This is the locus represented by this complex equation here. Now, if you want to look at it in more accurate form, I'm going to show it to you here. I'm going to bring out my GeoGebra here. Okay, and then we can look at how does it look like in this case. Okay, let me clean this part first. All right, this time let me remove the description one more time. Okay, and then I'm going to place it nicely over here. Let me clean it up properly. Right, now we need to have a circle. So let me get a new one here. Let me get it smaller a bit. Okay, this one, let me get a new one. We don't need to save this. So we need a circle. I can just key in directly into my GeoGebra here. So I know the center of the circle is at point negative 0.4. I just straight away convert it to decimal. It's easier. And then the other one is 2.2. Okay, now that is the center of the circle. And then this circle come with a radius of 5. So I'm going to draw a circle here. All right, circle point and then radius. Okay, so the point is A. Radius, I know that it come with a radius of 5 unit. And then there you have it. I'm going to make it smaller a bit. Now there you have it. This is a circle locus that is centered at negative 0.4 and 2.2 with a radius of 5 unit. And then there you have it. That's a wrap for these complex equations for pure mathematics 3 that you guys is going to see very soon. And then now the description to each one of the complex number can be found in the description section. Right, so do check out the description section on which past paper is that and then which question. Then you can refer back to the mark scheme just to check whether the number does tally. In case I make mistake, do drop do write down your comment. If there's any error, you can write down the correct answer in the comment section. Right, thank you very much. For those students who are taking pure mathematics 3, I would like to take this opportunity to wish everyone the best of luck. And then I'll be posting more of further maths videos, especially for all the components for further math students who are going to sit for the paper also very soon. Right? So best of luck until I see you again. Cheers, everyone.